Hello everyone and welcome to TLE Eliminators PCD for CodeChef Starters 227. This is Vibhaas Srivastav and today we'll be discussing all the problems from 1 to 5. So let's get right into it. Problem 1, buying tickets. Okay. Chef wants to buy tickets for a sports game. It has n total seats. Some seats have already been bought, so they are marked with S of I equals 1. If they're available, their S of I equals 0. And each seat costs A of I rupees. So what is the minimum cost chef has to pay to buy K seats? Each of the seats has some particular price A of I, right? N goes up to 100, K goes up to 100. So even though this can be solved in O of N, no matter what approach you use, pretty much you won't hit TLE, so it's fine. So let's see what the input looks like. N is the total number of tickets and K is the number of tickets which chef needs to buy, and you're given the value of each ticket, like the first ticket costs 4, second ticket costs 2, third ticket costs 6, fourth ticket costs 8, so on. And also you're seeing that the first ticket is already bought, second ticket is already bought, but third and fourth are not bought, right? And we're talking about the second test case here. So that's basically the input format. Okay, and we need to buy it as cheap as possible. We don't really care about anything else. So the approach to this problem should be very simple, I think. The only issue someone could have with this question is if you mess up the implementation somewhere, in which case you should really practice your implementation skills. Okay, so what do we need to do? Some tickets are unavailable, right? Some tickets are unavailable, right? Available, where S of I is equal to 1. Ignore those tickets, so you can remove them from the array, or you can make their value equal to infinity, or whatever you can do to ignore them. Ignore those tickets, right? It's given that in the impossible case we should print -1. So if the remaining tickets which are available are having a count less than K, then obviously it's impossible. So if the current count of remaining tickets is less than K, then we know it's impossible, so we can return -1. Otherwise we just need to find K tickets with the smallest sum, right? So we can just sort the tickets and print the sum of the smallest K. So sort the tickets, print the sum of the smallest K or the first K elements, print the sum of the first K values. Right, and this is our logic. Obviously the time complexity will be n log n since we're using a sort operation, but nothing else really needs to be done. So time complexity is big O of n log n, right? For n equals 100, obviously this will pass very trivially, no issues. Let's have a look at the code. Okay, so we input n and k, we have a vector of values which we input, and we have a string of s which we input. Either you can remove the values which are not available from the vector, or you can set their value to infinity. So that's what I'm doing here. I set it to int max, and if they're available, I increase the count of the available values. If the count of the available values is less than K, just return -1 and continue. Otherwise sort the vector and print the sum of the first K, right? So accumulate from the beginning to the beginning plus K of the vector. And that's about it. Pretty straightforward question. Let's move on to problem B. Okay. Problem B. You have n dice. Each has 6 faces. Values from 1 to 6 are available on each dice. You're also given an integer s. You have to do the following operation. Choose one face of each die. Basically choose one face of each die such that the sum of all the values is equal to s. Okay, and it's always guaranteed that you can make a choice where the sum is equal to s. All right, So let's summarize the question. It says, given n dice, choose a face for each dice such that sum of values on each face is equal to S. Now we cannot use this face again, or we are replacing the value of this face with 0, right? So mark this face as unusable for each particular dice. Now we need to again pick some faces from each die such that we can make a maximum sum, and this is going to be our score. Okay, now again pick a face for each dice to obtain the maximum possible score, but we cannot use the unusable faces, right? Maximum possible score. Okay, and this part is up to us. We can choose the faces from the remaining faces any way we want. So obviously in each dice we will pick the maximum usable face. N goes up to 100, again very small constraints. Even though it could be solved for much larger n, we have very small constraints. Okay, how do we approach this? So we'll break the logic down. For each dice, the face, we'll call it face of the ith dice, can be anything between 1, 2, 3, 4, 5, 6, right? And ideally we want to pick a face for each dice which is maximum possible, because in the end we want the sum to be maximum possible, right, in the second operation. So ideally we want the face for the second operation that we pick to be 6. Okay, we want the face in the second operation to be 6. This means that we don't want to use the 6 face unless it's completely necessary. Don't use f of I equals 6 in the first operation. Why? Because if we use it in the first operation, we cannot use it in the second one, right? So don't use f of I equal 6 in the first operation unless absolutely necessary. Right? That is going to be our observation. And if it is necessary to use it, right? If it is necessary to use it, maybe the sum is so large that we need to use the 6 to form that sum S, then we are left with being able to choose only 5, right? So if it is necessary to use the 6 face on a die, then in the second operation, while we're finding the sum, in the second op, we will choose the face of 5, right? So each time either we're choosing the face 5 or 6, we're not going to choose anything smaller because there's no point, right? Either 5 was used or 6 was used. Sorry, either 6 was used or not. If 6 was not used, we can always choose 6. If 6 was not used, if 6 was used, then we can choose 5, right? So that's how it works. Okay, so when will we be forced to choose the face of 6, right? When will we be forced to choose 6 as one of the faces, right? And if you think about sum of dice, each can give a value between 1 to 6. So then one dice can give between 1 to 6. So n dice can give you values between n to 6n, right? That is the possible sums which we can get, and s is in this range, right? N less than equal to s less than equal to 6n. And obviously if we could only use the values from 1 to 5, if only use the values from 1 to 5, if we only use values 1 to 5 for faces in the first operation, then we can make the sums between n and 5n, right? Because each face maximum 5, and then for all n faces n to 5n. If our sum is greater than 5n, right? So we can already get an observation. If our sum is less than or equal to 5 times n, then the answer is simply 6 times n, right? Okay. And if our sum is going to be greater than 5n, then we need to use the, if our sum is going to be greater than 5n, then we need to use the other, we need to use the 6 face for sure. So in the second round, we cannot use the 6 faces in some cases, right? So what is the minimum number of 6 faces we need? Well, that's also obvious. It's simply s minus 6n, sorry, s minus 5n, right? So the minimum number of 6 faces, we'll call that k, which is the minimum number of faces, which need to be a 6, right? So s minus 5n, that's exactly how many values of, how much value of s does it be larger than 5n, right? Because each of those will be a different dice becoming 6. And so in this case, so this is the case, right? So in this case, what is going to be our answer? We know that k values already used up their 6 face, so these k values can only be multiplied by 5, and the remaining values can still be multiplied by 6, so n minus k times 6, and this is going to be our answer, right? So for the case s less than 5n, s less than equal to 5n, we have 6n as the answer. For the case s greater than equal to 5n, if we define k like this is going to be our answer, right? And we can write this more succinctly in one case directly. We can write simplify, we can say k is equal to s minus 5n with 0, right? So in this case, k will simply be 0, and our answer will be equal to 5 times k plus n minus k times 6, right? K is the minimum number of dice which must show a 6 in the first term, right? And that minimum number dice is simply s minus 5 times n, or it's 0 if that value is negative, right? And that's it. This solution runs in big O of 1 for a given s and n, right? So time complexity is simply big O of 1, right? Okay, let's have a look at the code for this. So yeah, input n and s. Because n and s are small, we don't even need to care about using long log. We can just use integers directly. K, according to the formula, is max of s minus 5 times n and 0, and then we output the answer, which is 5 times k plus 6 times n minus k, right? So that's it. All right, moving on to the third question, problem C. Okay, an array B of size 2 times m is called good if adjacent elements are equal. Okay, so they have said 2 times I minus 1 and equals equal to b of 2 times I. So basically this means that adjacent elements are equal, right? 1 comma 1 is equal, 3 comma 3 is equal, so this is a good. B 4 comma 4 is good. 1 1 2 is not good because 1 1 is equal but 2 does not have anything to be equal to. First of all, it's not even sized, so it cannot be good. Okay, given an array of length n, find the longest subsequence which is good. Not the longest subsequence, find the length of the longest subsequence which is good. Okay, now there are several ways to solve this, but we will do the simplest approach, which is to use a DP. I think there might be a greedy method to solve this as well, but there's a pretty straightforward DP and that's what I used in the contest. So we're going to try that out. N goes up to 2 times 10 power 5. Each value goes up to n. So that's just, this just helps you use a frequency table if you want, but we'll see the solution with maps because the log factor does not really matter for 2 times 10 power 5. Okay. So let's pull up the solution. Let's write expected time complexity, right? And r and log n. This is the expected time complexity because n goes up to 2 times 10 power 5. Okay. So now let's try to understand what the longest subsequence could be satisfying the condition. Okay. So we need the length of longest subsequence satisfying the condition it is even length and adjacent elements are equal. Adjacent element means like 1 1 and then like 2 2 and then 4 4 3 3, these kinds of adjacent, not these two. The adjacent odd and even elements are equal, right? Like this, like the first is equal to second, third is equal to fourth, and so on. So that is the condition we need to solve, right? And basically many of the problems where you need to find length of a longest subsequence satisfying some condition, obviously the first thing that should come to your mind is a DP, right? Sometimes greedy will work because you are finding length and not the sequence itself, or sometimes it might work to just find the longest subsequence itself with greedy if the condition is sufficiently simple. But obviously your brain should first go to DP, try to think of some DP, and then see what pops up, right? Only the DP time complexity is too high. You might start thinking of some greedy ideas, unless obviously it's a very simple question. Okay, so how would you think in terms of DP, right? So in terms of DP, there are 4 main things: base case, state, transition, and the final case, right? These are the 4 main conditions of a DP which you must satisfy. And here, what is our state, right? Let's focus on the state first. We need to find the length of the longest subsequence satisfying the condition. So what we can say our state is, let's say this is the whole array of length n, and we can define our state as something like this. So for only this prefix, right, for only this prefix I, length I, what is the value of dp of I? Okay, and dp of I is going to be the longest solution in this prefix, right? Longest subsequence satisfying condition, satisfying the given condition in this prefix, all right. Now let's try to think about how we can rationalize, or how we can think about the transition for this given DP. Okay, so now the first thing we think about this DP is, it's kind of like a 2-state DP. Just the length of the longest subsequence is not going to be very easy to compute directly, because we need to ensure that not only this condition holds, but also like this condition is also holding, right? So what we're going to do is we're going to have 2 DPs. you can consider dp of I1, or we can call it dp1 of I, whichever you want to say, and dp I2. Okay, and this is going to be basically the length of an odd length sequence satisfying this condition except for the last element. Okay, so length of the longest one satisfying this condition except for the last element, and we are going to ensure that last element is equal to ith value. Ensure that last element is equal to a of I. Okay, this is one more condition in our dp which will help us simplify the problem. Okay, and what will dp of I2 be? It will be the one where everything is paired up, right? Everything is paired up, and last element is equal to a of I, right? So then we can just take max of all the values of I for dp of 2, and that will give us our answer. So this is just a simplification which helps us, right? So our final answer, so this is our states, final answer is gonna be dp of max of I going from 0 to n minus 1 over dp of I 2, right? This is our final answer. Okay, so if you're not quite understanding this, pause the video, try to go back, carefully understand what I'm saying, or maybe you can wait until I show the code and try to understand from that. The code is pretty simple for this. Okay, so now we need to ensure that the last element is equal to a of I in both. So that's just a simplification, and also the longest chain where it ends at an odd value, and the longest chain where it ends at an even value. And in the odd case, the last one does not matter, but everything else should be paired up. In the even case, it's the full problem, everything should be paired up, right? Okay, so then for the odd chain, dp of I 0, right? That is simply, or we're calling it 1. Okay, dp of I 1, that is simply going to be the maximum even chain we found so far, right? The maximum even chain we found so far in 0 to I minus 1, right? The maximum even chain, or the maximum value of dp of I2, which we have found in this range, plus 1, and the 1 is just this odd element, which is our current element, right? So that is simply going to be max of right? So this is for the odd chain. Okay, now for the even length chain, now we know, let's say we had, let's say, a 4 over here in the array, then it can't be paired with 5 or 3 or 2 before it, right? It must be paired with a 4. Now if it's getting paired with a 4, it just needs to be paired with the 4 which comes just after it, right? So if there are multiple 4s here, there is no benefit in taking a 4 which is farther away. We only need to take a 4 which is just before it, I mean the nearest 4 just before it, right? Because this part of the chain will be independent, and then we can choose the longest chain which comes before, like this, right? So that's what we need to do. So we can say that for the even length chain, our answer will be dp I2 is equal to the previous occurrence of the current value. So the previous occurrence of this value, and let's call that previous of a of I, right? So let's say dp of previous of a of I, previous occurrence of a of I. Let's say previous is a map, which gives for each a of I the previous occurrence of a of I. We can maintain this map as we go on. 1, right? Why 1? Because at this previous value we want the length of the longest odd chain, right? And then we can add the current value as well and make it an even chain by adding a +1, right? And these are our two DP transitions, right? DP transitions. Okay, so here we discuss the two states, right? The two states which we want, and here we discuss what the final answer looks like, and here we discuss the two DP transitions which we need. This transition obviously can be done in O of 1, right? O of 1, we simply maintain the max as we go along. This transition can be done in O of log n if we use a map for previous, right? If we use a map. O of 1 if we use hash table. If we use hash table, right? Or frequency array. Hash table or frequency array is O of 1. In my code, we'll use map just to be simple. So the code will be n log n. Okay, and what are the base cases? The base case is just DP of 0 we can have, or DP of like the starting element. So we can just have base case length will be equal to 0, right? So DP of whatever the base case, you can say -1 or 0 or whatever, that's just going to be 0, right? Because there is no, if there are no elements, basically the base case is array being empty, and if the array is empty then DP values will be 0, right? That's it. Okay, so let's have a look at the code. Yeah, one modification we can do is, instead of directly storing the DP array, like this, the way my code has done it in my code. So I'm just explaining my code, because if you implement this, obviously it will pass, but my codes did it slightly differently. What we did was we stored, instead of having what is the index of the previous element, we just stored the DP of the previous element directly, right? So we stored DP1 of previous element was a map, right? Was a map. So that way directly we just stored the value of DP1 of the previous element. And also DP2 is also a map in my code. There's no reason for DP2 to be a code, to be a map, but that's how it is. Okay, so these are just some quirks of my code. Obviously it's better to implement with frequency array or hash table and make it run in O of 1, but the way my code is, it's n log n. Okay, let's have a look. Code is pretty simple. So both our DP1 and DP2 tables, I have kept them as a map, and our answer is going to be the prefix maximum of DP2, which we're going to print as our final answer as well. Okay, so now for each element x, we input it. If this value exists in our DP table, DP1 table, or DP1 map, then we can do the DP2 update, right? DP2 update is basically whenever this previously occurred, find the DP value and add a 1, right? Which is exactly what this code does. So even though my implementation uses map and is a bit inefficient, the code becomes much cleaner. And then DP1 of x is just answer plus 1, right? And why is it answer plus 1? Because as you can see, our final answer is just prefix maximum of DP2, and this transition also prefix maximum of DP2, so we can just do answer plus 1. And then finally answer is the max of current answer and DP2 of x, so we're updating the prefix maximum, and finally we can print the final answer. So very short and sweet code for a, you could say, relatively complicated problem. Obviously I think there might be some greedy way, but then my challenge to you is to write a code which solves this problem, but is shorter than this, right? Shorter than from here to here in the main function. All right, let's move on to problem D, or the fourth problem. Problem D. Okay. personally this was a fairly hard problem. I think problem E was easier than this for some reason. That's what I felt. But also you could say the ideas for this were standard, so could make sense. Okay, but yeah, this is also going to be another DP question, so lock in with your DP skills. Okay, an array B is called good if twice of each element is less than the value of the next element. So 1 comma 3 is good, 1 comma 2 is not good, 1 comma 2 comma 3 is not good. Okay, so for example we have 1 comma 3 comma 7 comma 20 comma 32. So this is good, right? This is good. But if this was 13, this is not good, because this is 14 and this value should be 15 or higher, right? And that's the definition of good. Now for a given sorted array B, the length of the longest good subsequence is just the subsequence, longest subsequence which is good, right? So from 1 to 3 we can obtain 1 3, which is good. Now given a sorted array of length n, we need to find the sum of f of c for all subsequence of a which are not empty, right? So all subsequence we need to find the sum of f of c. So basically and also we need to find it mod whatever, so we need to use modular arithmetic, so that's fine. So basically the question says for all subsequence of a, sum of length of largest subsequence of that subsequence, right? Of that subsequence such that the condition holds, such that it's good, and the condition is basically let's say our chosen values are b of I, then 2 times b of I is less than b of I plus 1, right? And this is basically what our condition is. Okay, maybe there's a simpler approach, but my approach does use a bit of combinatorics as well as DP, so yeah, it can get a bit messy. I recommend following through very carefully. Okay, so I'm assuming you've already read an example. If not, pause and read an example, understand the question, because we'll need to think about it carefully. N goes up to 10 power 5, a of I goes up to 10 power 9. Okay, so first of all we need to figure out what is the longest length of a subsequence which satisfies the condition. Okay, so one idea you can get is because each time b of I's value is doubling. Okay, so this is the crux idea. Without this I don't think you can solve the problem. Crux idea, which should be obvious because you see 2 b of I less than b of I plus 1, is that b of I values must be greater than doubling each time, right? Must be doubling each time, right? And also we know that a of I is less than equal to 10 power 9. So basically even if you start at 1, you go to 3, you go to 7, where each time we're choosing the smallest option possible, then 15, 31, 63, 127, so on. This doubling is going to be very fast, and at most we will have ceiling of log 2 a of I terms, right? So at most our subsequence length is going to be the maximum value, basically the maximum largest subsequence that something can have will be at most this length, right? Where it's log 2 of 10 power 9, right? Let's have a look at how big that is. So Desmos calculator, let's pull that up and see what we get. Okay, log 2 of 10 to the power 9. Okay, so we see that the maximum sequence can be at most about 30-ish. Right, the maximum sequence can be at most about 30-ish. Okay. So let's just take 32 as a nice number. It's going to be less than or equal to 32. Okay. So how does this help us solve the problem? Okay. So now we can imagine, because we need a sum over all subsequences and n goes up to 2 times 10 power 5, we need an n log n type of solution. Obviously, if you have 2 pointers or some kind of brute force, that's going to fail very miserably, right? So we are going to have to use some kind of DP again. Like if you have solved such problems before, you will have the intuition that we have to somehow use the count of subsequences which come before or after, right? Count of values of subsequences, right? Subsequences which come before or after to update for the current value, right? So let's say this is dp of I, and we have to update dp of I, which is the values of starting at the current value, right? Okay. So the way we are going to do this is we're going to think about the value at the current index. Okay, the value at the current index we're going to do in reverse order, because each one can double, right? So a of I can only take values which are at least 2 times a of I plus 1 or more, right? 2 times a of I plus 1 or more. So only in this, and that's why that gives us the hint that we need to do this kind of in reverse order, because these can only extend the chains which come afterwards, right? There might be some forward way to think about this as well, where this extends the chain which come before, but here we're going to do it in reverse. Okay, so let's try to see how we can break this down. The value at the current a of I is equal to x, and let all the subsequents which start at x, they're going to jump to some which start at a of I, they're going to be jumped to some a of k. Okay, so if a of I is equal to x, then a of k should be greater than 2x, or a of k should be greater than equal to 2x plus 1. Okay, and we can assume that any of the sequences formed from a of k plus 1, a of k plus 2, and so on, those can be increased by 1, right? Those can be increased by 1 if we include a of I. Okay, that's basically our idea. So let a of I equal to x, assume a of I is included in our subsequence for sure, right? Included in our subsequence for sure. Then the next element, if it exists, right, the length can only be greater than 1. Next element must be some value greater than equal to 2x plus 1. Okay, and that will correspond to some k. So imagine if we already have a pointer at I which just goes from right to left, we can also have a second pointer k, right? So 2 pointers kind of approach, which also trails exactly to the smallest value, which is 2x plus 1, right? So one pointer here which is at a of k, one pointer here which is at a of I. The a of k pointer is exactly at the value which is 2x plus 1. Okay, So now we are assuming that a of I is going to be included, right? So what we'll do is we'll calculate, we again use a DP idea. So DP of I is equal to including the value a of I as the first element, find the answer for all subsequences, right? Find the answer for all subsequences, and our final answer, because any value can be the first element, right? Any value can be the first element. So our final answer is simply the sum of all dp of I for I going from 0 to n minus 1, right? So this is going to be our final answer, and this is going to be our dp state. Okay. These questions are pretty mathematical, so it's quite hard to explain the intuition other than saying that practice dp and practice how to figure out formulas and make them relate to each other in the transitions. So it's kind of hard to exactly explain the intuition behind this because it's just math and analytical math. But I hope you can pause the video whenever you get stuck. Try to refer to the code and see how this all fits together. Okay, and follow. All right, because by the time you're solving a question like this, you should be having a decent grasp of dp, maybe even up to 1500 dp plus combinatorics, right? Okay, so assume a of I is included in a subsequence. The next element can be greater than or equal to 2x plus 1, so that is our k pointer. Now let's go back to this diagram. So this diagram is the key to our whole problem, right? So then a of I is included for sure. We will do some combinatorics, so that is in one way, right? One way, so it has to be included for sure. All the elements between I plus 1 till k minus 1, these may or may not be included, and the thing is they don't really affect our answer, right? They don't really affect our answer, so they may or may not be included, and the number of values which are there is basically 2 to the power k minus I minus 1, right? Each can be included or excluded, so that's two ways for each element in this range, right? So these are the total number of ways. There are total k minus I minus 1 elements, so 2 to the power k minus I minus 1 ways to pick elements from here, and this is for a length exactly of 1, right? This is for a length exactly of 1. Now if we want a length exactly of 2, right? If you want a length exactly of 2, that means that we can pick some other element from here, right? Some other element from here, and then find the number of ways to get dp of k1, right? So for length exactly 2, we need to find dp of k1 sum from here, right? And for length exactly 3, we need to find the next element dp of k2, right? So let's write down our dp transition. Okay, dp transition, let's change the state a little bit. So dp of k and dp of I j, and what will our j represent? J will represent the length of the longest good subsequence of our chosen starting at I, right? Starting at I. So find the answer for not all subsequences, but subsequence such that the length of the good subsequence is j, right? Good subsequence is j, and we have, this is very key, we have already showed that maximum length good subsequence will be at most 32, right? At most it will be 32, so that's why this will be only n into log n dp, right? So I and j are only n, I goes up to n, j goes up to log n. So at most it is n log n states. And so we can change our final answer as well. It will be sum of all I and all j such that dp of ij, right? Yeah. Okay. Let's just write this neatly mathematically. Sum of I, sum of j, dp of ij. I goes up to n and j goes up to 32. Okay. Let's get back to how we were transitioning, right? So j is our length, I is our current position, right? So how will we find dp of I1? dp of I1 is simply going to be 1 into 2 to the power k minus I minus 1, right? So this is simply going to be, k is a pointer which we already have, so it's going to be 2 k minus I minus 1, right? K minus I minus 1. Okay. Now for length 2, like value 2 for the subsequence, how many ways can we choose that? Well, that is simply, again, it's 2 k I minus 1, but now we need to multiply it. And what do we need to multiply it by? We need to multiply it by either choosing this as the next element and using dpk1, or choosing this as the next element, choosing dpk1, and so on. So we can write it multiplied by the sum of let's call it k dash starts at k and ends at n, dp of k dash 1, right? Similarly, dp of I3, and here you might want to pause and understand why this formula is happening, right? Will be again sum of k starting at k dash. Obviously we have a pointer to k, so we know where to start at, plus dp of k dash 2, right? Each time it's 3, so we already have one element from this, and then we need to find now the sum of length 2 subsequences starting at k dash. That's why it's length 2 over there, right? And that's how we can write our transition. So, and so on and so on till dp of I of maximum length is around 30, so we can keep it till like 31, and we can find the same transition. Let's write this neatly. This will be dp of I j is equal to 2 k is equal to first index such that, which we are maintaining with 2 pointers again, like I said before, first index such that a of k is greater than 2 times a of I. Okay, so that is k as equal to 2 times k minus I minus 1 multiplied by the sum of k dash equal to k up to n, or up to n minus 1 to be precise. Up to n is also fine, because in the end we can have an empty array, and over there a size 0 subsequence, which will be our base case, right? So that's why it's fine to sum to n, and we can write it as dp of k dash j minus 1, right? And this is our transition. If you implement this, although you will get the correct answer, and obviously make sure to use mod, right? Make sure to use mod. If you implement this, you'll get right answer, but you will also get TLE, right? You will get TLE. Why will you get TLE? Because although the number of states is just n log n, right? This is n, this is log n. The transition itself is not n log n. Why is the transition not n log n? This can obviously be pre-computed. So this can be found in O of 1, right? So that's not an issue. But this is the issue, right? We are taking a sum from k dash to n, and that could be another n elements, right? N elements checked in the sum. So our time complexity for this would be n squared log n, right? Time complexity would be n squared log n, right? So n squared log n, worst case, right? Worst case. How do we optimize this? Okay, first of all, if you want, you can implement this till this idea, or you can just start thinking about how to optimize this. I'll give you a minute to think about how to optimize from here. Okay, and the solution for optimizing DP, obviously there are many advanced techniques to optimize DP, but there is the very standard way. And the standard way, whenever you see a sum, is obviously use prefix sums, right? That's our good old friend prefix sums. So use a prefix sum, right? Use a prefix sum. Use a prefix sum, right? All we need is the sum of, for each j minus 1, we need the sum from k to n, right? We need the sum from k to n. So we can just write it as, let's say we have a prefix sum version of the DP, which stores the sum of, or not exactly prefix sum, suffix sum in this case. So let's call it suffix sum, suffix or prefix, whatever you want to call it, suffix from k of j minus 1, right? And then if we maintain this suffix sum while going on, then this will also be O of n, O of 1 over here, right? O of 1. So our transitions will be just O of 1 time. So the overall time will be n log n, because that's the number of states. All the transitions are O of 1, right? And this will be our AC solution for this problem. Obviously pre-compute this also for faster time. If you take log n to compute this, it will be n log n squared, but we will pre-compute this for fast solutions. Okay, and what should we note from this? Yeah, one more thing we can do for optimizing it is, instead of storing the suffix sum for starting at k, we know that if we are already at k, if our k pointer has already reached k, then we don't need to store the suffix sum of k plus 1, k plus 2, so on, because they will never be used, right? So our suffix array only needs to have 32 values, one for each j, right? One for each j. So each time we just move the k pointer using two pointers technique, we will just update the suffix sum, so we can drop this part, right? So we can just make it suffix of j minus 1, right? Suffix of j minus 1. And that's it. This is our final solution. Our base case will simply be dp of n. So n is beyond our array. Our array is 0 index, so 0 to n minus 1. dp of n, so completely empty suffix, has a length 0 subsequence, so one of them, right? That can be our base case, or we can say our base case is suffix of 0 is 1, right? And that will maintain our base case. Okay, let's have a look at the code. How do we implement something like this? For someone who is not that comfortable with DP, this would be a kind of a nightmare, but yeah. Okay, so first of all, we are pre-computing powers of 2, right? Very standard pre-computation. Go to this code carefully. We have to use the modulo m over here, right? So each time we do power of 2 equals power of 2 minus 1 times 2 modulo m, right? This is how you pre-compute powers of 2 for some mod. We can't use the power function because that uses double. It can give us incorrect results. Also, it is very slow. So that's why we pre-compute these powers of 2. Okay. Now for each test case, we input our array and we make our DP vector. Yeah, so there is a slight error in my code. I'm not sure how I got AC, because as I explained to you, the maximum length can go up to 31, right? The maximum length can go up to 31 because a of I goes up to 10 power 9. A of I goes up to 10 power 9, and as we saw, the log is 29, so it can go up to like 30 or 31 length. But yeah, so we should make sure our vector is at least that much. So yeah, everywhere j goes up to 32. I'm not sure how I got AC, but yeah, you should change it to 32 because that's exactly the log. Okay, maybe there's a tighter bound on the length, or maybe the test cases were weak. Maybe they'll add a better test case later, but yeah, up to 32, right? And our dp vector is n into j, so that's n into 32. Okay, also this is going to be our suffix sum array, right? Suffix sum array which starts at k and goes up to the end. It suffix sums for each length j, right? So in this I call it prefix sum, so that's prefix sum. It also has 32 values, and as our base case we put the length 0 subsequence occurs exactly once, right? So that's put here. K is starting out as n in the start because for the last element k points to some point outside the array. Okay, so starting from the last element and going to the first, we will decrement using two pointers approach k if possible, right? So while a of k minus 1 is greater than 2 times a of I, decrement k. Also make sure to update the prefix sum array or the suffix sum array while we do so, right? So we just add the dp, make sure to take mod, and we continue decrementing. Okay, now the part where we update our dp, so this equation will be implemented. Dp of ij is the prefix sum, right? So this part of j minus 1 multiplied by the power of 2 of k minus I minus 1, right? Multiply with the power of 2 of k minus I minus 1. Yeah, and our final answer is going to be the sum of this dp of ij. One thing I messed up, which I forgot, is that each j is going to count the number of subsequence such that the length of the good subarray is j, right? So it's going to be the number of subsequence here. The number of subsequence which starts at a of I has the length of the maximum good subsequence as j. It's going to count how many number have this, right? So then each of these will give us a weight of j or a contribution of j. So we have to multiply by j for finding the final answer, right? So dp of ij times j. So sorry about this, I should have mentioned this from the start, but very important that we're multiplying with j, right? Because we just don't want to count how many are there, we also need to find the sum of f of b, right? So far our code is just counting that starting at I, how many subsequence are there whose value is j. We don't just want the count, we want the sum of the values, right? So we have to multiply each count with the value itself, right? So our final answer is going to be sum of I, sum of j, dp of ij times j, right? Because the length is j and the length of the good subsequence is j, and this gets added to our answer. Okay, so I times j, dp of ij times j, and for each dp of ij which we have visited, we are just adding this to the answer. Take answer model. Finally, when all of this is said and done, we can print out the final answer, right? So that's it. Right, yeah, it's a bit of a complicated problem. Maybe there's a simpler approach which I didn't think of, but I think this is a very organized approach for someone who knows dp, and it should be somewhat understandable, I think. Yeah, it's a fairly hard question, like at least 1600 plus, so I'm surprised to see so many solves, but yeah, at least 16 to 1700 plus. So I don't think anyone below expert might be able to attempt such a problem unless you're very good with dp, or there is some simple approach which I'm missing. All right, the final problem, tree sets, problem 5. Problem 5. Okay, yeah, this is a much simpler problem than 4 to me. Just some combinatorics, just some 2 observations in combinatorics are going to be used here. Given a tree with n nodes, a non-empty set S is called good if the following condition holds. For every pair of nodes which are unequal, right? For every pair of nodes which are unequal, there exists some node such that the path from y to z, this pair, passes through x, right? So for every pair in the set S, there is one common node x which comes on the path. That is the question. Okay. Uh, how do we approach this? So let's break this down. N obviously goes up to 10 power 5. So n or n log n kind of solution. So yeah, we're given a tree, right? So let's just draw a tree. And let's see. Okay. So let's see some given two nodes. Okay. Now these two nodes, if they have a path, it passes through this. Okay. And let's say this was our set S. We can say, okay, one of this is the common node, one of this is the common node, this can be the common node, right? If only these two are the elements in our set. What if this is also an element in the set, right? And as soon as there are three elements in the set, there can only be one possible common node, right? Which is the, basically in this case, it will be the LCM of all of them, right? And this will be the common node between all of them, right? So this path, and this path. Okay. Now what if additionally there was this node in the set? Okay, so the set is all the elements marked in blue, right? So our set is the all the elements marked in blue. Now here this path goes like this and this path goes like this. So there are two paths which don't have any common nodes, right? So basically valid sets, let's just remove the blue here. Valid sets all paths between nodes, pair of nodes goes through the common node, right? All paths between pairs of nodes goes through the common node, and that is a key condition on valid sets. Okay, right, that's literally what is given in the question. Or all paths between pair of common nodes has to overlap at least at one node, right? Has to have overlap at least at one node. Overlap at least at one node, at least at one node, or even better we can write it as no two paths are disjoint, right? No two paths are disjoint. No two paths are disjoint. So now we're still figuring out the problem, so we should look at the graph and see what patterns are there. Now obviously if you have a set of size 1, right, set of size 1, it automatically satisfies the condition. If you look at the test cases, it automatically satisfies the condition because there is no pairs you can make. So all the paths are going to be the same, right? Same starting point, same ending point. So this will trivially satisfy the condition, right? What about set of size 2, right? Set of size 2, that also trivially satisfies the condition. All the paths which go from here to here, there's only one path, so all the nodes can be valid x, right? All the nodes on this path can be valid x. Okay. Now what about set of size 3, right? Set of size 3. So in a set of size 3, either we have one path like this, one path like this, right? So then there is a common node between these two paths. Or let's say all three paths are like this. So we have a common node, which again is their LCA sort of, right? So their LCA is always going to be a common node. Now, as we showed, there are possible sets of size 4 which don't work out. Like for example, this and this have no common nodes between their path, right? So the way we're going to think about this is to fix the common node. Okay, fix a particular node as the common node. Okay, and let's assume that's the root. Okay, let's assume that's the root. So the root is the common node. Root is the common node X. Okay, common node X. Okay, so now in order for this root to be the common node, what's going to happen is that if let's consider each subtree separately. Okay, so this thing forms one subtree, right? So let's just draw with the green dotted line the first subtree, right? Let's draw with the green dotted line the first subtree, right? And let's draw with the pink dotted line the second subtree. Okay, and let's draw with an orange dotted line the third subtree, right? So if this is the root and these are, we're assuming that the root has to be the common node, right? So the way why we're doing this, we're simplifying the problem. Each node can be considered as the root, right? Because a tree can be rerouted so that each node can be considered the root. And if you consider the current node as the root, it gets split up into these subtrees. And if the root has to be the common node, that means that in the subtree, there can't be, in a given subtree, there can't be two nodes at the same time, right? Because the path over here will not include the root, right? The path over here will not include the root. So two nodes cannot have a common path. Like two nodes cannot be in the same subtree, right? So that means that from each subtree, at most one node can be chosen, right? At most one node can be chosen from each subtree. That's correct. Okay. So let's just decide on that. We can say that from this subtree, let's say there are S of A nodes here. Here there are S of B nodes, and here there are S of C nodes. Let's just denote with their own colors. S of A nodes, here S of B nodes, here S of C nodes. Okay, and also in all these sets, the root also may or may not be chosen, right? So that is just S of 0, which is 1, right? So either the root is chosen or not chosen. The size of this subtree kind of is 1. So now let us write the number of ways to choose. Now let us write the number of ways to choose. Number of ways to choose. Number of ways to choose valid sets such that the root, which is node X, is going to be the common node on the path. Right? So how can we do that? We already showed that from each subtree, at most we can pick 1, right? So let's say we picked 1 over here, or we can pick 0 also from a subtree. Similarly, we picked 1 over here, 1 over here, and we can maybe pick or not pick either the root itself, right? So each gives us some number of choices. Let us write the equation for this. So we can say that the number of choices is going to be S of A plus 1, Y plus 1, because either we can choose any of the given S of A nodes, right? So S of A is 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 ways to pick a node over here. Plus 1 because we can pick none of the nodes. So that's a plus 1. So S of A plus 1 multiplied by S of B plus 1, S of B plus 1, multiplied by s of c plus 1, right? S of c plus 1. Okay, s of c plus 1. Cool. Where s of c, s of b, s of a are the count of the subtree sizes, right? And also we can take the root or not, so that's again another two choices, right? So that's simply 1 plus 1, right? Okay, now if we just multiply this out, we will get the number of ways, but this will also have, for example, the case where, like, if you multiply this one, like, don't choose this with don't choose this with don't choose this with don't choose this, then we have a case where none of them are chosen, right? The set size is 0, and that's not possible, right? It says non-empty set. So subtract the non-empty set from this equation. Okay, now what if we find for each node we can take as the root? We can use like a rerouting kind of idea to find the subtree size, right? Subtree sizes can be found with DP, so I hope you know these facts. I'm not going to explain them. If you're not sure about this, then you should learn DP graphs a little bit more. But facts, subtree size can be found using DP, right? Subtree sizes can be found using DP, right? And rerouting can be done in O of 1, right? Rerouting is simply O of 1, because if you want to consider, let's say, this node as the root, okay, if you want to consider this node as the root, then all you need is the subtree size of this, subtree size of this, subtree size of this, and this whole this part, right? This part over here becomes another subtree if this is the root, right? If this has become the root, that is simply n minus s of x, right? So it's a subtree of size n minus s of x. So basically you're able to reroute the whole tree so that this is the root and we have all the subtree sizes in hand in big O of 1 itself, right? So this is some theory you should know, right? Rerouting D for subtree size. Okay, so why can't we just directly sum up this value for each node, right? And the reason is we are going to overcount. Why are we going to overcount? Because what if like, what if we did not choose a value from two subtrees, right? What if we did not choose the value from two subtrees, right? Let's say like this, we only chose a value from, let's say, this subtree, right? Now the issue with this is when we are counting with this as the root, then this will get counted, right? And then when we're counting with this as the root, this will also get counted. When we're counting with this as the root, this will also get counted, right? So no matter what the root is, it's going to count everything again. So the only way we can prevent overcounting is that we will not allow basically we will not allow any other root to have a set of size 1, right? To have sets of size 1, set of size 1 not allowed, right? Size 1 not allowed except for the root, right? Except for the root, right? So total n minus 1 nodes are there, n minus 1 nodes except the root, and we will subtract n minus 1 from this sum, right? So let's write this sum and subtract n minus 1. We had already subtracted 1, now we're going to subtract n minus 1. So basically that's the same as subtracting n from this sum. Okay, so we are writing this sum and we subtracted n. Are we done? Have we prevented all the overcounting? No, there is still one more overcounting left, and that is what if we had pairs? Okay, so let's say we have a pair like this. We know that all the nodes in this path can be a possible common node, right? This can be a common node, this can also be a common node, this can also be a common node. So each time when this is the root, it will count it. When this is the root, it will count this set, and when this is the root also, it's going to count this set. This issue only happens for sets of size 2, right? Sets of size 2, never of sets of size 1, right? Only happens for sets of size 2. And basically yeah, it only happens for sets of size 2. And for sets of size 3, we always know that there's a unique common node for sets of size 3 or more, right? So we will never have this issue. But sets of size 2 are going to be counted twice, not twice. They're going to be counted as many times as the number of nodes on a path, right? So if these are the two values in the set, it's going to be counted here, 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 here. Each time these can be valid common nodes. Each time when we run this this formula, it's going to count each of them. So basically what we can say is we are only going to count it if and only if we are on the highest one, right? If and only if we're on the highest one, we'll count it. When we go down, we are not going to count those nodes, right? We're not going to count those values. How do we do that? Right, when we go down, we're not going to count those values. So basically we are going to punish all pairs between we are going to punish all pairs which are forming between our current node. Let's say this became the root and this became everything above, right? This became everything above. Let me draw with blue, dark blue. So this is the root, this is the whole subtree which is above, right? This is the above subtree using rerouting which we are doing. This is one of the bottom subtrees and this is the other bottom subtree, right? Let's give it a different color than the root, red. So these are the three subtrees which are formed where this is the root, right? So any path between the upper subtree directly to the root, that is already counted by the upper subtrees, right? That is already counted by the upper subtrees. So we are going to ignore such paths. So we can penalize all pairs between the root and anything from the upper subtree, right? And so let's say the last subtree was subtree upper, right? Subtree upper, let's say the subtree formed by all the nodes above me, and I will subtract that value as well, right? Subtree upper, each node from subtree upper can form a pair with my node, and in fact it can form a pair with any node below me as well, right? So this can be an intermediate value on the path. This can be an intermediate value on the path, like from upper to this value, right? So any pair of node which forms from above me to less than equal to me needs to be penalized. So subtree upper times subtree of the current node x, right? And this gives us the final formula, right? Where we have removed all the overcounting. It's a very pure combinatorics problem with rerouting. Not exactly even DP. Rerouting can be considered a greedy kind of idea as well, right? Or pure logical idea. It's pure combinatorics. So for each node x, we have the sizes of the subtree computed somehow, either with DFS or DP or whatever, right? Let's say n. Okay, so these are the sizes of its subtree, and the upper subtree which is formed for all the nodes above it, that has the size of n minus subtree size of x, right? These are the sizes of subtree of children of x, right? Now we are going to count all the possible sets where x is a common node without overcounting, right? So overcounting in the sets of size 1 and overcounting in the sets of size 2, as well as not counting the set empty set, right? So the formula is simply going to be answer will be equal or will be summed, right? So the final answer will be the sum of basically s of a plus 1, s of b plus 1, so on, s of n plus 1 times subtree of upper plus 1 times 2, right? Because the current node can be chosen or not chosen, so that's always 2, right? So sum of this value subtracted with n subtracted with subtree of upper times subtree of x, right? And then this equation summed for all the x nodes using a rerouting DFS gives us our answer, right? implementation time, big O of n, right? Because we can do dp in big O of n, we can check all the neighbors, multiply them in big O of n. Similarly, all this can be done in big O of n. So the time complexity is big O of n, right? Make sure to use mod, right? Don't forget, make sure use the mod. All right, let's have a look at the code. Main function first, or let's think about the variables first. We're just defining the mod long here. N, final answer. This will store subtree sizes. This will store adjacency list. Input n, change the adjacency list to have n values. Input the edges. Answer is 0 at start. Each subtree is assigned with 1 because obviously a subtree has the node itself. So the subtree sizes are assigned with 1. Do the DFS and print the answer. Okay, what happens in the DFS? DFS has x and the parent, so we don't revisit the parent, right? On a tree, we just need these two values. So value will store the current value of this node, this value, which is going to be summed up. Starts with 2 because the 2 term is always there. Now we will do this multiplication. So for each adjacent node, if it's the parent, just continue. Otherwise, do the DFS and calculate its subtree size and values. Subtree size of x increases with subtree size of the child, standard subtree size dp basically. And also value increases with subtree of y plus 1, right? Subtree size of y plus 1, we multiply by that. Make sure to mod the value. Now the size of subtree of upper is n minus subtree size of x, so that's written here. Value gets multiplied by upper plus 1, right? So subtree size of upper plus 1 gets multiplied over here. Mod the value. Now we need to subtract n over here from the value, so we subtract n. This removes the side 0 sets and size 1 set except itself. That's what it does. Now we need to remove the size 2 sets from everything above, right? Size 2 sets from a node here and any node here. So that's all the subtree size of upper and the subtree size of x, right? So we subtract that from the value, take mod. Now this is the answer of, this is the value of this particular node, right? So this is the value of this thing for this node. The final answer is sum over all nodes. So we just add it to the sum mod, right? And we can print the final answer. So pretty pure, almost combinatorics question on a tree. So nice combinatorics on a tree. All right, this brings us to the end of the session. It's pretty late for me right now, so I'm going to end it here. Do upsolve the questions, right? So my usual advice, always, even when you hear the solution, upsolve it, especially since today's questions, especially the last two, are kind of implementation heavy. Implementing it will really get you a proper understanding of what's going on. And do check out the TLE Eliminators self-paced course. Obviously, we have discussed this many times, and I think if you're stuck around to this point, you would already know about it. So go check out the TLE Eliminators course on the website. Alright then, thanks for watching and see you in the next PCD. Bye bye.